Hello, good day, sir. Good day, friends. My name is Eliakub Nuruddin Saleh with number 006 and Pasiku Binat Oluwole being my partner on this presentation. And specifically, I'm going to present on the topic locating an earthquake center, epicenter here, which is a very crucial topic as seismology is concerned. First, here is the outline on this presentation. We are going to be covering on some seismological terminologies, the introductory aspect of it. Then we have a guide on how to read earthquake wave graph, because all the analysis that we'll be making is based on a kind of graph. Then we have seismometer, we have introduced seismograph and seismogram, and some crucial steps to be taken in locating an earthquake. Then the first thing we are having here is the definition of some terminologies. The epicenter, which is just a location on the earth surface directly above the focus. We have a fault, and we will soon be looking into what a fault means. We have hypocenter, we have lag time, and seismogram. We have seismometer or a geophone, which is responsive to the ground movement. So here actually is the focus of an earthquake. If we assume this is a homogeneous isotropic medium, this is a ground surface, so here is the point of a rupture called a focus, and here is the epicenter, that is the point immediately above the earth's surface. So seismology is the study of waves generated and transmitted through the earth, and we all know an earthquake is defined as a sudden motion or trembling. We call it a tremor in the earth, which is caused by the abrupt release of a strain on a point, and the shaking from an earthquake travels away from the rupture in the form of seismic waves. So what we are saying is, we are going to be looking briefly into some causes of an earthquake from the perspective of a fault. You can see here is a kind of fault. So fault is a sharp break in a crustal rocks. Rocks near a fault tend to move in the opposite direction. In that case, that causes a friction and gather a lot of pressure. But at some point in time, the movement will overcome the friction, and the rocky materials slides or tends to slide over past one another, and that results in a release of a large amount of energy, and we refer to it as an earthquake. So the point immediately where the point where the rupture occurs, we refer to it as the focus of an earthquake, and the point immediately above the surface of the earth where it occurs is called the epicenter of an earthquake. And the epicenter is actually the central part of this very presentation. So, as we have said, earthquakes are caused by seismic waves. So there is need for us to go through briefly into what a seismic waves are and their classification. So the seismic waves are just any kind of waves that you can initiate, that you can travel or you can propagate through the earth's surface. You can, through a rocky material, you can time it as not necessarily a wave that originated in the rocks. You can as well set up a wave to propagate through a rock, and we call it a seismic wave. So we have two broadly kind of waves, seismic waves, which are the body waves and the surface waves. And the body waves are basically the waves that travel to the interior of the earth, and they are in turn classified into two: the P wave and the S wave. P wave is nothing but a primary wave. The P there stands for primary waves, and these waves are the waves that move by alternately compressing and stretching materials in the direction of waves. That is, in the direction the wave is traveling. They are like, in fact, they are transverse waves, because we learned that transverse waves, in case of transverse waves, waves moves move the particles in the same direction as the wave is traveling. So these are actually what P wave does. And we have S wave. They are the body waves that move with a shearing motion, that is shaking particles from side to side. And we can link this one with the transverse with the longitudinal waves, because when the longitudinal waves move, the particle direction is perpendicular to the direction of the travel of a wave. And we have surface waves here. The body waves reaches at surface some of their energy. That is, when the body waves reaches the earth's surface, some of their energy is transformed into surface waves, which travel along the earth's surface. And we have two kind of the Rayleigh waves also, which is R wave, or two kind of a surface wave. We have Rayleigh wave and we have lobe waves. And the Rayleigh wave are characterized by a vertical motion of the ground, like ocean roll if it is propagating. So we can term lobe waves. They are characterized by side to side motion. So that is with regards to, and we have this is basically the picture or an idealized model to demonstrate how these waves propagate. These are the four main kind of waves. This is a P wave, and as we have said, when the wave, this red arrow is indicating the direction of a travel of a wave, and as you can see, this is an idealized model of a homogeneous surface. This is the ground surface. As you can see, when the wave is passing, it is like compressing and expanding the particles in the same direction. This is the undisturbed medium where the particles, where the waves are yet to reach. And we have S wave, which is the longitudinal wave, and as you can see, the wave moves perpendicular. The particle move perpendicular to the direction of the travel of the wave. This is a lobe wave and this is a Rayleigh wave. So quickly let's go into into this. That is on how to reading an earthquake graph or an SP curve graph, because we are going to be working on this kind of graphs, whether they are taken from, in fact they are taken from the seismograph. So here is just a common graph that we all know. We have y-axis, which is representing a time axis, and we have x-axis, which is representing a distance to the epicenter. So this is actually a reflection of what is happening on a seismogram. The time here is calibrated in minutes, from 1 to 24 minutes here, and the distance is calibrated in kilometers, as you can see, from 1 to 2 up to 10 kilometers. We have two curves. The first curve is a P-wave curve, which is the fastest event that register at seismic recording location. Then this is the second curve is the S-wave, which is the second event that normally register itself at seismograph. So here is just an example on how to use this kind of graph to make a meaning on the information concerning these P waves and S wave or radar. Here is the first problem is how long did it take a P wave to travel 4,000 kilometers. So when we are given this kind of problem, we are going to be using what we have been given. Here we are given 4,000 kilometers. The question asks us about time. How long did it take a P wave? So basically, we are going to be using this kind of curve, the P wave curve, because the question is targeting at P wave. So this is a P wave curve. You say, how long did it take a P wave to travel 4,000 kilometers? So quickly we just go to where is 4,000 kilometers here. So we extend an arrow that touches the P wave curve. At the point where it touches, that is the tangent at which the arrow we have drawn from the horizontal axis. So the point at which it touches the P wave, then we now refer to the vertical axis and see how, and see the time on the time axis, and see the number of minutes. So as you can see, here is it requires 7 minutes to travel a distance of 4,000 kilometers, and you can still make some meaning out of this one, because you can see that for the same distance, to cover the same distance, an S wave, which we consider with that we consider a wave that travel with medium speed, which is less than a P wave but greater than all the surface waves. So we can see that for an S wave to reaches 4 kilometers, it has to travel additional, getting to 6 minutes. As you can see, it requires 13 minutes here to travel the same distance that has been covered by P wave in 7 minutes. So the second problem is, what was the distance covered by an S wave in 14 minutes? So we are given the time information, so we quickly go to the time axis and we locate our 14 minutes. We now extend an arrow that touches the S wave curve, since we are talking particularly on S wave now. So when it touches at the tangent, you now extend an arrow vertically that will touches the horizontal axis, and that particular point is the distance that is required for an S wave to travel in 14 minutes, which is 4,500 kilometers, as you can see. So apart from that one, we have lag time, and lag time is nothing but difference, just the difference in the time of arrival of the first P wave and the first S wave. We care about this kind of waves because they enable us to make meanings concerning or to make our analysis. So here is just an example. We have two curves as usual, the P wave curve, which is the first event, the second event. As you can see, the time interval between this is just the wavy-like pattern, or we call it a seismogram. So it's from this seismogram that we identify the arrival of these waves. This is a P wave and this is an S wave. So the difference between the time interval is 5 minutes. So automatically we will now say the lag time for this one is 12 minutes, which is the secondary wave time arrival, minus 7 minutes here, which is the P wave arrival. It will give us the 5 minutes. Then we have seismometer, seismograph, and seismogram. We have already explained this seismometer, because this seismometer is just like the normal geopon that we all know. It's an instrument that detects, or that is responsible, or that responds to the ground motion. And we have a seismograph here. Seismograph is an instrument which is combined with seismometer with a device for recording seismic waves. We are going to see one. Here is just a 3-dimension view of what? Of a seismograph. Then we have a seismogram, which is just a graphical output of a seismograph. Then so here is a typical seismograph, and as you can see, this is the working principle in its simplest form. The instrument consists of a frame or housing that is firmly anchored to the ground, and a mass is suspended from the housing and can move freely in a spring. So actually, when the ground shakes, the housing shakes along with it, but the mass is designed in such a way that it will stay fixed. When the ground shakes, the frame and the anchored, or the base, tends to join and shakes, but this pendulum will remain fixed due to inertia. A pen attached to the mass, we can see that this is just a pen that is writing on top of this rotating drum. It's just a pen that is attached with the mass, a pendulum mass. So when the ground shakes, this pen will not shake, but as the rotating drum along with the anchored are shaking, then it will now be drawing a wavy-like pattern based on time in function, as a function of time and amplitude. So we'll be having this kind of pattern, and it is this kind of pattern that we refer to as a seismogram. So this is a typical seismogram that we will just talk about. As you can see, this is the P wave arrival, this is an S wave arrival, these are the surface waves, but we care more about these two waves because they are the fastest seismic waves, and the difference between the time of arrival of these waves is called a lag time, as we have explained. So coming to the instrument and the steps in locating an earthquake, there are some instruments, because we need calculator, we need metric ruler, we need compass, we need a colored pencil, and mostly the primary colors, the red, blue and green. We are going to be talking about on how to make use of all these instruments. So here are the steps. Here are the steps to be taken in order to get the epicenter of an earthquake. The first thing to do is to determine the arrival time of P wave, the first P wave and the first S wave. After identifying them, this is just like normal identification. You identify the arrival times. After that, you now calculate the difference or the lag time that we have just explained. You calculate the lag time between the arrival of the two waves. Then you now refer back to the earthquake time graph and determine the location on the graph where the two lines have a difference in their y value equal to the difference you previously calculated for the lag time. So the x value at this location is the distance to the epicenter of an earthquake. Very soon we will see looking at one example. So here is a problem of finding a distance to epicenter. Suppose the P wave arrives at t equals to 1 minute and the S wave arrives at t equals to 6 minutes. So we can see the question is now asking us to determine the distance of the earthquake's epicenter. So the first thing to do, as we have seen, the steps to be taken. The step one is to identify the waves. What is the identification of waves? We just have to take what we are given here. The arrival of P wave is 1 minute and that of S wave is 6 minutes. That's all. We identify them. The second step is find out the difference or the lag time between the arrival time of these waves. So here is 6 minutes minus 1 minute. It will give us 5 minutes. Then step 3, we will now refer. Okay, there is one thing we do. Once you have calculated this lag time, you are going to draw an equivalent unit of what you just calculated. This is 5 minutes. So each unit now is representing 1 minute. So you are going to create an arrow of 5 unit lengths, and you are going to take that particular arrow and make sure you keep the 0 axis on top of your at the bottom of your P curve. What we will be doing is we are going to lie this arrow until it perfectly fits between the two curves, that is the P wave curve and the S wave curve, and exactly at a place where the two curves fit this arrow. Then we now refer back to the distance on horizontal axis, and that will give us actually the epicenter of an earthquake. So as you can see, when we drag this arrow from here, it was able to perfectly fit in between the two curves at what distance? This is almost 3,400 kilometers. So we can now say the earthquake have an epicentral distance of 3,400 kilometers, and that's all. Then here, in an extension to the other one, because when we talk about locating an earthquake, it's just like calculating a distance. We don't know here the only information that we can get is the distance to where the seismograph is 3,400 kilometers, but we still need to know exactly this earthquake happens along the north, in the east, or in the south direction. So to do this, we still need some additional information, and that is why we are having this example, because we are going to be making use of 3 different seismographs. the readings from 3 different seismographs will be used in order to identify the exact location where the earthquake occurs. So here is here we have like 3 different seismographs. The first seismograph is in Tepic, which is in Mexico, and the lag time has been calculated to be 1.5 minutes. The distance to epicenter is 900 kilometers. The second seismograph is in Isla Socorro, which is the same Mexico, abbreviated as SOCO. The lag time in their seismograph is 3 minutes. The distance to epicenter is 1,800 kilometers. This is Peninsula in USA. Pennsylvania in USA, sorry. The lag time there is 5 minutes, and the distance to epicenter is 3,300 kilometers. So what we will be doing, since we have identified the lag time and calculated the epicentral distance for the tree, the next thing to do is we are going to get a map that will cover from Mexico up to USA, that will cover the 3 different seismic stations here. And actually this is just the problem. As we can see, this is the first seismograph, the second seismograph, this is the third seismograph. This is 1.5 minutes, 900 kilometers away from where it records from where the rupture occurs. This is 1,800 kilometers from where the rupture occurs. So the rupture actually occurs here. This is the farthest distance from where the rupture occurs, and it is the third seismograph. So we are going to be drawing for each one. We are going to draw a cycle with a radius equal to the epicentral distance, which is being measured by a particular seismograph. And when we do so, at the end of the day, we will discover that there is a particular point where the 3 seismographs, or where the 3 cycles meet, and that particular point is what we are talking about. That particular point where the 3 waves intersect is actually the point where the rupture occurs. Here is the typical example. This is the first seismograph, which is 900 kilometers from the rupture point. So you can see, as you can see, that we have radius of 900 kilometers. Here we have radius of 1,800 kilometers in SOCO. This is a seismograph in SOCO, was able to detect an event 1,800 kilometers away. This is close to where the event happened, and it is 900 kilometers. This is the farthest seismograph in this example, where it has 3,300 kilometers away from where the rupture occurs. So this is our map, and we are able to, if we are able to detect or to point a single point where the 3 waves, where the 3 cycles intersect, then that particular point, then we refer to our map and see where is it. Then is the exact point where the earthquake or the rupture or the tremor occurs, and that is this. So conclusively, the shaking from an earthquake travels away from the rupture in the form of seismic waves, and these seismic waves are classified according to where they travel and how they move the particle as they travel, and we have to explain that one. And basically they differs in propagation speed, and that is why we are able to make a lot of analysis on these waves. The 3 seismographs are needed to locate the epicenter of an earthquake, and each station will determine the time interval between the arrival time of the first P wave and the first S wave at their particular location. If we have it here in Abuja, it will only determine from here, from the location here in University of Abuja to where the rupture occurs. The travel time graph then determines each station's distance to the epicenter. We have seen this one. Then we refer to our map. On a map, we draw a cycle around the seismic stations, and the radius of the cycle equals to the distance to the epicenter. We now repeat for other seismic stations. We call this process a triangulation, and it is not necessary that 3 seismographs must be consulted. We can decide it to, because the more we gather a lot, the more we are able to make a good estimation on the exact location where the earthquake occurs. So the 3 cycles will meet at a single point, and that point is the epicenter of an earthquake. And that is all about our presentation. Thank you for listening.